Assalamualaikum and good day to our lecturer and GAs. We are from Group 4 and now we're going to present about the windy field. Our group consists of 3 members, me, myself, Nur Intan Batrisha, Farah Ashura and Muhammad Azri. This is our table of content. For this presentation, we will go through 28 pages. So firstly, the overview of the windy field. Windy field is located about 270 kilometers north-northeast of the Kemaman supply base. It is within the northern east part of Malay Basin. In pre-1980s, early explorations of activities within Malay Basin was done. Next, the lithology of windy field mostly consists of sandstone. In this project, we were required to study on 2 wells in the subsurface of windy field, which are Windy 1 and South Windy 1 well. From the earlier studies, the well data produced by Windy 1 and South Windy 1 shows that both were gas fields. For the project outcomes, we expect to evaluate and interpret the geological structures and features of windy field subsurface by using the well data from Windy 1 and South Windy 1 to be able to produce subsurface map of Windy 1 and South Windy 1 by correlating seismic data and well data. Third, to be able to perform horizon picking and fault picking and interpretation based on the generated map. Fourth, to be able to generate seismic data between 3D seismic data and well data from Windy 1 and South Windy 1. Lastly, to be able to learn and use spectral software for seismic studies. Well, for the project workflow, firstly, we import data to Petra. Then we do the seismic data and well calibration. Next, the horizon picking and fault picking, then conversion of surface map, then we do the interpretation and the conclusions. Next, the methodology, which is similar with the project workflow, which are firstly, we import all the data to the software that we are using, which is Petrel. We import the seismic and well data. The seismic data includes the SEGY and inline and crossline data, while the well data includes the well top, well log and check shot. Then we calibrated the seismic before seismic interpretation. Under seismic interpretation, we started to do the horizon picking and fault picking. For the horizon picking, we determine the horizon from well data, then pick 50 units of inline and crossline, then complete the horizon and interpret stratigraphy. Fault picking, we find major or minor faults perpendicular to inline and crossline. Interpret fault structures. After we're done with the seismic interpretation, we managed to create several surface maps, such as the time domain and depth domain surface map. From there, we identify the geological structure, seismic phases, and the outcome of the surface conversion. Now I'm going to pass the floor to Farah Ashura for further explanation.
Now I'll present more about the seismic stratigraphy of our seismic session. Here I have provided you the view of our wells and well tops from the 3D and interpretation window. On the 3D window, you can see the Bundy well, which is marked with a blue circle, and South Bundy well, which is marked with a green one. If you look at the interpretation window and cross line 3084, it shows us the well tops views, which is E32 SST. On this slide, this is what we can observe once we've done our horizon and fault picking. At the interpretation window of crossline 3184, the green, orange, and purple vertically slanted lines represent the fault picking, while the horizontal blue line shows the horizon picking. Before we start horizon picking, we have to identify which line in the seismic well can represent Bundy and South Bundy. After careful observation, we made the E32 SST horizon as a marker, and this is where we began our horizon picking. On the 3D window, on the other hand, it shows us all the picked horizons and faults with an increment of 50 for both inline and crossline. As you can see here, my team and I managed to identify 4 faults relative to the strike direction. The way that we identify our fault is by observing the direction of the strike. From there, we then decide on whether having the fault picked on inline or crossline. Now here shows the picked faults on the surface map relative to depth and time. The difference between depth domain and time domain is the unit, where depth domain uses meters and time domain uses milliseconds. This map provides us a better view of the faults that were picked. Now the picked faults on the surface map can then be converted into fault surfaces, which helps us recognize the shape of the fault, either it is flat, curved, or any other shape. In depth domain, the elevation range is between negative 3,250 meters to negative 250 meters, while the elevation range for time domain is from negative 2,500 milliseconds to negative 250 milliseconds. On this slide, we can see the map window of the surface map, which shows us the details of the map such as the legend, info box axis, and scale bar. For depth domain, the elevation is from negative 1,950 meters to negative 1,350 meters, and the elevation for time domain is from negative 1,750 milliseconds to negative 1,300 milliseconds. It can be observed on both maps that the northeast area that is represented in red has the highest elevation, while the west area, especially southwest, represented in blue or purple, has the lowest elevation value. Next, we have the 2D surface map, which shows us more about the structure of the map, such as faults and contour values. Here I have marked the faults with a black curved line, though it should be noted that not all faults can be seen on the map surface. The red arrow, on the other hand, represents the dip of the fault. The table below shows the dip angle, dip azimuth, displacement, length, and height of each fault. From this surface map, it can be seen that 3 of the faults is picked at the northeast area, while 1 fault is picked at the west area. Then we have the well section of Bundy and South Bundy. A well section is used to display well logs in specific order, which includes the available logs and well logs. Lastly, we have synthetic generation, which acts as the fundamental link between well data and seismic data. And it is the main tool used for geological picking and is associated with reflections in the seismic data. However, the synthetic itself can't be generated on the Bundy well due to systematic error. As for the South Bundy, there are fewer information. Next, I'll be passing the floor to Azri to explain further regarding the findings of the maps generated.
Assalamualaikum and hello everyone. My name is Mama Azri and I will present about the discussion on the findings of the maps generated. So let's start. The first structure that we have identified on the map is a channel. Channel generally is a linear depression on the surface of the earth which water and sediment can flow through. There are 3 types of channel, which is straight, meandering, or braided. As you can see in the slide provided, there are two same type of channel, which is meandering channel that we have found on the map. We continue to the next structure, which are onlap and downlap. Onlap basically is a pattern of reflections that we can found on seismic data that mainly occurs during periods of transgression, while for the downlap, it is the termination of more steeply dipping overlying strata against a surface or underlying strata that have lower apparent dips. As you can see in the picture, the upper side arrows are showing the onlap formation, and for the below arrows, the three arrows shows the downlap formation. Next is pitfall. Pitfall, there are two types of pitfall, which are pitfall associated with velocity, mainly occur because seismic data are presented in travel time rather than depth. The second one is pitfall associated with geometry, which they are occurring because reflections from a three-dimensional space are plotted in a two-dimensional section. As you can see in the two picture given, the first one is fault shadow in the circle that usually occur nearby a fault, and the second picture is showing diffraction on the seismic data that we have gained. Continue to the next finding, which is graben. It is elongated block of the earth which is occurred between two faults, and usually it is facing downwards. As you can see in the picture given, there is graben that occurred between two major faults, and it is facing downwards relative to the blocks on either side. The next finding is sequence stratigraphy. Sequence stratigraphy is a branch of sedimentary stratigraphy which is mainly deals with the order or sequence which is related to strata succession in time versus rock units. As you can see in the picture, there are four sequences. There are sequence 1, sequence 2, sequence 3, and sequence 4, and continue with the next sequence if they have got other sequence. After that, in the seismic interpretation window, we have found the folding formation. Folding basically is an undulation or wave in the stratified rock of earth crust. Stratified rock originally formed from sediments that were deposited in flat horizontal sheets, but in a number of places the strata are no longer horizontal but have been bent or forcibly been bent because of depressions. In the first circle, you can see in the picture that I have given, there is a type of anticline folding, and beside it, it is the syncline type of folding. There is hydrocarbon potential in the seismic data that we have gained, which is identified based on the bright spot. In reflection seismology, a bright spot is a local high amplitude seismic attribute anomaly that can indicate the presence of hydrocarbons and is therefore known as a direct hydrocarbon indicator. It is usually used by geophysicists in hydrocarbon exploration. As you can see in the picture given, there is a bright spot occurred or exists nearby a major fault. For the recommendation section, we think for fault areas, we should prefer to use smaller increment to make it more details and specifically shown. The second recommendation is low data quality. It is maybe because of during data acquisition, weaker frequency is being used. As you can see in the picture given, there is very little seismic data in the interpretation window, and for this problem, we can use stronger frequency to avoid this problem. To conclude, for this seismic project, we are using Bundi and South Bundi wells. Compression occurred in most of the area and causing several formation of major faults. Due to the faults, there is accumulation of hydrocarbon trapped mainly nearby the fault form. The small amount of oil trapped in Bundi area is probably because of the oil is migrating from other group of formation where carrier beds are available in Bundi area, and the oil migrate through the carrier beds laterally towards the flank and fill up the traps at the basin margin.
So that will be all from Group 4. Thank you for your kind attention.